Hey everyone, I'm Ravi Lucky Reddy, and I'm joined by Joshua Tang and Alex William from Poolsville High School, and we're going to be talking about electrodialytic recycling of phosphogypsum into sulfuric acid. So phosphogypsum is a byproduct of phosphoric acid production, or the fertilizer industry. So solid phosphate rock is reacted with sulfuric acid to produce phosphoric acid and phosphogypsum. Currently, over 1 billion tons of toxic phosphogypsum it has accumulated in Florida. And it can't be pumped underground because it's solid rock, and it can't be repurposed because it contains radioactive materials, and the EPA prevents that. And about sulfuric acid, it's used primarily for fertilizer production, but it's versatile and can be used in many other industries. However, its current production has many flaws. So sulfuric acid is produced in bulk through the contact process, which is incredibly harmful to the environment. So the first problem is the release of SO2 into the atmosphere, which is a contributor to acid rain and water pollution. And it also requires a lot of energy, leading to higher costs because we require fossil fuels to be superheated. And issues with phosphogypsum and the contact process include radioactive stacks of phosphogypsum collapsing into the water supply via sinkholes, due to Florida's porous limestone. And the porous limestone also leads to phosphogypsum seeping into the groundwater supply and nearby water bodies, causing eutrophication.
Okay, so electrodialysis is a splitting of dissolved ionic compounds into their cation and anion components. So basically what this means is that we have calcium sulfate and from our gypsum, and as you can see in the diagram on the right side, we're splitting sodium sulfate, which we get from turning calcium sulfate into sodium sulfate with sodium hydroxide. And by splitting it into the two parts, using like electrostatic interactions, which is basically pulling like a positively charged ion towards the negative side. And ion exchange membranes are basically like synthetic membranes that only allow a certain type of ion to pass through. So as seen in the previous diagram, we're able to pull off sodium and sulfate into their respective chambers, allowing for us to concentrate sodium hydroxide and sulfuric acid separately over time. We can summarize this process into three chambers, with the electrolysis chamber being the one where you have like new sodium sulfate being like pumped through continuously, and that's where it gets separated into like both sides. So due to EPA regulations and public controversy, oh, whoops, I forgot to switch. So due to EPA regulations and public controversy regarding its radioactivity mixed with everyday life, it is currently piled up in stacks, crusting over as it dries out. Its impurity poses numerous problems in everyday usage, as it is difficult to decontaminate it, which is crucial for potential production of fertilizer from it.
And now we will move on to actual cells. So these are prototype cells, and as you can see, they worked on either two-chamber or three-chamber designs. For example, this is a two-chamber one. And these cells did work. However, the current efficiency was low and provided a lot of resistance and wasted a lot of electricity. However, some sulfuric acids was still produced, as can be seen in the picture to the top right corner. Next slide. Yeah, and here's our final cell design. As you can see, we have an adjustable voltage controller, and we use a large cathode to maximize the current efficiency and minimize resistance. And we use an anode made of graphite, which can resist corrosion in the highly corroding environments. Additionally, the cell is heated to provide less resistance, and it is constantly monitored pH, so we can track the progress of the cell as it's going. And it's three-chamber also. Keep going. And here's the data. As you can see, the pH of the catholyte and analyte, which both constantly decrease over time, and the current increases over time, showing an increased separation of the two salts, creating higher conductivity. And we produce 10 milliliters, so it's a pretty good yield. Yeah. And we analyzed the final product, and there was a small amount of contamination. However, it was all able to be removed and purified. Keep going.
Okay. Okay. So if wait, sorry, that's yours. Oops. So if implemented on a larger scale, our method has the potential to revolutionize the sustainability of its chemical industry as it gives a green way to produce a valuable commodity from waste and simultaneously perform carbon capture, preventing a global warming. Furthermore, our method is much cheaper compared to conventional methods, increasing the likelihood of business owners supporting it in future implementation in Florida.
Because that's time. Real quick, one more sentence to conclude.
So a cell runs effectively only on electricity and converts industrial waste into a useful product, and can be made to a very cheap cost, as well as capture carbon in the environment.
Okay, thank you.